At the bottom you have the memory map, so here you have to define the master and the slave in the systems, and at what address you can access such and such IPs. So basically everything you do with this GUI can then be done by scripting. So you have one feature which is also really convenient, is that you can log into a file all the steps you are doing with the tool, and a TCL file is then produced, and you can then script or make copy paste from this file to produce subsystem, or reuse in fact already the things you did. So what is the platform we did? So the platform was based on two cores. So the first is this embedded vector processor. So this guy was dedicated to do the chip rate processing. So for example, you have a slave rate receiver that was previously in hardware, and that was then now software on these cores. Master reg here that is monitoring the primary common indicator channels, and so basically all the chip rate done on this core. So it was around 22K lines of EVP C code, which is a mix between pure C and with some mnemonics dedicated to this guy. On the other side we have the modem controller. So it was a Cortex R4, and all the control parts ran on that. So this was dedicated to the symbol rate processing. So here it was 15K lines of C code. So you can see here the second de-interleaving, the transport channel demultiplexing, first de-interleaving, direct matching, and the CRC detach. So all this processing chain is described in the 212 as mentioned before. And so basically at the bits you have at the output of the CRC are what we call a transport block set, and so these blocks are then returned to the layer 2. So here we see the AXI interconnect on this picture. So in fact the AXI was the bus used for the real IC. For us, as I already mentioned, we used a simple PV bus at the beginning. Then some dedicated IPs like shared memories, interprocessor communicator. Here we have the 3G outer receiver acceleration. So on that we had the VPU, the Viterbi processor, which was not software but an hardware blocks. Also the turbo decoders, and same things for the transmit pass. Okay, so here we see IQ samples and the radio interface unit. So I will show you the contents of this block. So basically we first validate the software using IQ samples produced by a link level simulation chain. But this is enough in the case you do a static test. When you enter some more complex use case with dynamic exchange, I mean when you have to transmit also in TX some information, you will be really limited by such way. So this is why then we had a connection using a reference tester. So I have some slide later on that will explain what is this tester. The tester was coming from a NIT, and so basically you exchange the IPs using UDP packet over the network, and you have a PC for sure to drive the tester and run your tests. Okay, so here we see the link level simulation. So we had the Node B, which is a base station, in fact, simulator. Yeah, some RF channels, so it means that you can mimic fading, relay fading, or such things, and then produce your samples. So how we started? In fact, we were only 5 people in this team. So 3 software engineers, so myself and 2 other guys. So I was the project leader of this platform, and 2 architects. So the architects, yeah, those guys knows exactly what we had to put into the platform, and so we just started by typing in some C or C++ code. And also one person was a designer that comes with a VHDL background. So we first had a look to the host key and say, and SystemC, okay, it's nice, but you have a lot of things to do by yourself. And as I already said, we really wanted to have something up and running quickly. So we say, okay, no way, we have to use ESL tools, and this is why we go through Coware. So we also have to learn the SCML methodology, play with this new object, see what we can do with PCT, with SCID, and things like that. And also, it's yeah, a new way of implementing behavior, because yeah, the guy coming from VHDL wanted every time to instantiate, in fact, blocks. And you see, for example, that you will see later on in the radio interface unit that we had DMA inside the block, and those DMAs were just typed in line, in fact. And we could also decide to reuse a SystemC DMA component and to instantiate it into the block, but we did not do that. So this is why, in fact, you have to think about your design and find the right way between, yeah, okay, you know what I mean. Okay, so just a few words yeah, on that. Yeah, at the beginning the designer was a little bit scared by C++, but in fact you do not really play with all the concept of C++. You just use the main one, which is yeah, inheritance, and then it's exactly the same framework which is used to define your SC modules with your ports, the registers bank, and so on. So it's quite straightforward to set up. And concerning the program, so we were a new small team, and part of the program as other core business like algorithm, IC, and yeah, firmware software, and so on. So the inputs we need, so first what you need is the use case that the end users wants to target. So okay, some use case come from the 3GPP specification, other ones are yeah, customer independent. You need to know what are the speed you target, and to define some milestones as ever. What is really important is to have a clear functional yeah, unit diagram, so some objective specification with the registers mapping and a global memory map, in order to know in PCT what are the address you have to put. Yeah, we reuse a lot, in fact, of algorithm from a link level simulation tool. So you need, in this case, the C code for sure, and the input patterns and output patterns you expect, in order to first validate your block unitarily, and then you plug that. I mean, then you had yeah, same other IPs to create subsystems, and you go up from ground to the final solutions like that. And if you need to run drivers on top of that, or OS, you also for sure need that.